He's doing the PhD on supernova environments, and he will be talking about this project that we are doing. He has been visiting for 2 weeks. He's leaving tomorrow, right?
Yeah. Yeah.
Unfortunately.
Yeah.
Yeah. But well.
Yeah, thanks. So yeah, as Luis said, I'm a PhD student at Universidad Diego Portales in Santiago, Chile. And I'm also doing this studentship at ISO. And today I will talk about these two projects that I've been developing in my PhD. The first one, where I analyzed this very interesting event called Supernova 2011 FH. And I'll talk a bit about it, about this class of transients called supernova imposters. And then I will also describe the project that I'm doing right now and working with Luis, where I'm analyzing the environments of core collapse supernovae with observations from the MUSE instrument. So, oops. So yeah, as Luis mentioned, I'm working with Jose Prieto and Joe Anderson, which are my main advisors in these projects. Also, many other people are involved in this work from the amusing collaboration and from the ASAS-SN survey, which I will describe a bit later. And of course, many other people that are collaborating. So let's start with 2011 FH. This was my first PhD project, and it was this very curious event, which is part of this class of transients called supernova imposters. So first I'll talk a bit about interacting transients. So when some supernovae, they happen inside these very dense medium, very dense material that are generated by previous explosions and ejections. When the ejecta of the supernova interacts with this circumstellar material, it will generate these very characteristic emission lines that we observe in their spectra. So the shocked circumstellar material will generate these broad emission lines that we observe. This will hit the gas around it, and the heated gas, the ionized gas, will produce these narrow emission lines that give name to the type 2N supernovae and the type 1BN supernovae. So the type 2Ns are the ones with a hydrogen-rich circumstellar material. So we see the hydrogen in the narrow emission lines of hydrogen, and the type 1BN supernovae, they are in helium-rich circumstellar material. So we see these emission lines of helium. Not just supernovae happen inside these very dense environments, but also other stellar explosions, such as these violent eruptions in luminous blue variable stars, such as the famous case of Eta Carina, which is this luminous blue variable in the Milky Way. It is surrounded by this very dense material around it. And in the 19th century, it generated this very violent explosion. And we could see again these very characteristic emission lines of interacting events. So the problem is that in some cases, these stellar eruptions that are not supernovae, they are misclassified as supernovae because they are very similar to real type 2N supernovae. So here I put two cases, supernova 1998S, which is a type 2N supernova, and also 1997BS, which was classified as a type 2N, but then people found out it was a supernova imposter. So it was a stellar explosion, the star was still alive, it didn't end up in a supernova. The spectra of them are very similar to each other, but there are some hints, some clues that we can identify to see which one is an imposter or a real supernova. For example, the real supernovae, they are much hotter. So they have like a bluer continuum. They have broader lines indicating larger velocities of the ejecta. Also, supernova imposters, they are less brighter. So they usually have this magnitude of -14, while type 2N supernovae, they are much brighter. They are -18, -19, -20. Then we had this supernova, 2009 IP, which was famous because people until today, they still cannot decide whether this was a real supernova or not. So this was a very ambiguous event that presents both characteristics of imposters and of real supernovae. So let me explain a bit about it. It was discovered in 2009 in this first outburst when it reached a magnitude of -14. And at that time, people already were discussing whether this was a real supernova or not, because it presented very high velocities. So velocities of around 12,000 kilometers per second, which are characteristic of type 2N supernovae. But 1 year later, it presented another outburst. This one here, the second outburst, showing that actually the star was still there. It was still producing these very violent eruptions. So the first outburst was not a real supernova. And then in 2012, it presented these two eruptions. The first one here, also reaching -14. And the second one here, when it reached -18. So then people start debating again whether this was the real supernova or not. Some arguments for the supernova case argue that this was a very bright event. There was no non-stellar eruption that reached that much luminosity. Also, it reached again very high velocities, but other people argued for the imposter scenario, such as the low amount of nickel 56 needed to explain the light curve of the event. It was very low. And also the fact that they didn't detect any material that is usually produced in supernova explosions. So after 2009 MP, other events that were very similar to 2009 MP were discovered. And we realized that actually these types of events are very common, and which is bad because we cannot define whether they are a supernova or not. But every time we discover a new event, we have like a new clue, a new hint on their nature. And that's the case of 2011 FH, which was discovered in 2011 by an amateur astronomer. And actually, most of the light curve of the event, which I'm showing here, the R-band light curve, was obtained by this amateur astronomer in South Africa. So I think this is a very interesting part of the project, that they are providing data for these analysis. And 2011 FH has this very interesting light curve with some properties, such as, well, the peak brightness was of around -18 in absolute magnitude, which is very similar to 2009 AP. We see this brightening event. So the star was getting brighter and brighter for around 6 months when it exploded in this major eruption. We also see that the star was very bright before exploding. So these are like 3 or 4 years before, and we can detect the star in the galaxy. And also we see the light curve after the explosion is very is declining slowly, which is because the ejecta is still interacting with the circumstellar material. So as I mentioned, this is an event very similar to 2009 IP. And here I'm plotting the light curve around peak of 2011 FH in orange, and of 2009 AP as these pink stars, and also 2 other similar events. Just to show how similar they are, well, they have a very similar brightness at peak. They all reach this -18 in absolute magnitude. They all show this precursor event. So in some cases, they show this very short explosion. And in other cases, such as 2011 FH, they show like a brightening of the star in the months before the main eruption. In some cases, we also observe these bumps in the light curve, which is the ejecta interacting with many layers of the circumstellar material. and they all evolve very slowly with time. So 5 years later, 2011 FH was observed by the Hubble Space Telescope. And it was surprising to see that, well, the source was still there here in the outer layers of the galaxy, and that it was still very bright. So we measured absolute magnitude of -13, around -13 in this F814 band of Hubble. And this is very similar to Eta Carina in its great eruption. So this might be telling us that the star is still there, that the explosion of 2011 was not a real supernova, and that the star is going through this eruptive state. Or the other possibility is that, well, that was a real explosion, a real supernova, I mean, and that they're still interacting with the circumstellar material. So this HST data was interesting because we could detect stars around the source, around the 2011 FH, and we could use the photometry of these stars to estimate the age of the stellar association of the stellar cluster that is part the progenitor of 2011 FH. So here I'm showing this color magnitude diagram. The red dots are the sources detected around 2011 FH, and this gray shadow is a model color magnitude diagram obtained from this code BPAS, which is this stellar evolution code. So we fitted the data, the stars that we detected to this color magnitude diagram. And then we used this other code called Age Wizard, which give us an estimate in age. So a window in age of the fitted data to the color magnitude diagram. And we found the median age to be of around log 6.6, which is around 4 million years. So, and this translates to a mass of 60 solar masses for the progenitor of 2011 FH. And this mass is actually the same that was estimated for the progenitor of 2009 AP. Another interesting feature of 2011 FH is that at later times, this was a spectrum obtained, so almost 1400 days after 2011 FH explosion. And this spectrum shows many similarities with other supernova imposters, and also with LBV eruptions such as Eta Carina Great Eruption. So we see that they have the same age alpha width, so the same velocities as 2000 CH, which was a famous supernova imposter. They also have like similar temperatures, similar black body declinations. And with Eta Carina, they share these strong calcium emission lines. So just to finish this part, we have like many possibilities of what could have triggered the explosion of 2011 FH. This could have been caused by this unstable fusion, which is thought to be to operate in the outer layers of these very massive stars. So stars with masses around 100 solar masses. Well, binary interaction is also a very strong possibility because this is what is thought to have happened in Eta Carina. And we know that more massive stars have a larger probability of having a binary companion. Well, this pulsational pair instability is another possibility that is also thought to operate in very massive stars. And also this could have been a weak supernova. So a star that collapsed directly to a black hole do not produce a strong explosion, but we see this very weak interaction with the circumstellar material. So if you want to know more about this event, more analysis and more possibilities, you can check out the paper. I think the questions will be at the end, right? Yeah, so I can move to the next project. So yeah, so this is the project I'm working on right now, that I'm working with Luis, in which we are analyzing this data set of galaxies that hosted core collapse supernovae detected by the ASAS-SN survey. So just to give some context, I talked about these type 2Ns and type 1Bn supernovae, but there are many types of supernovae, and these types can be classified according to their spectra, so to the elements that are present in their spectra. Well, the most classical classification is between type 1s and type 2s. Type 1s that do not present any signal of hydrogen, and type 2s that have this these emission lines of hydrogen, such as we see here. And later on, people, with more observations, people are finding other sub-classifications of these different supernovae. So, for example, for type 1, we know now that there are type 1As, 1Bs, and 1Cs. Type 1Bs, they do not show hydrogen, but they have these very strong helium absorption lines. And type 1Cs, they do not show hydrogen or helium, but they have features of silicon. And as I mentioned earlier, some supernovae, they interact with this very dense circumstellar material, and we see these emission lines in their spectra. So if the circumstellar material, again, is hydrogen-rich, we see hydrogen in emission, like here. And if it's helium-rich, we see helium in emission. But what is important is that these different properties of the different supernovae, they are telling us that there are different progenitor stars and different explosion mechanisms for each supernova type. So a very early analysis of the different supernova types was made by looking at the galaxy where each supernova exploded. And people realized that types 2, 1B, and 1C supernovae, they only happened in spiral galaxies and in the star-forming regions of these galaxies. And type 1A supernovae, they happen both in spiral galaxies and in elliptical galaxies. So this is telling us that, well, these types of supernovae, they are related to younger stellar population, because younger stellar populations are only present in spiral galaxies, while type 1A supernovae, they are related to more older stellar populations because they are present in both types of galaxies. And in fact, all the evidence points towards this scenario. So both models and all types of observations, they tell us that type 1A supernovae, they are generated by the explosion of a white dwarf. So there is a white dwarf in a binary system. It is accreting material from this companion star. And when it reaches the Chandrasekhar mass, it explodes and generates a type 1A supernovae. And in the case of type 2 supernovae, they are generated by the core collapse of these red supergiants. So stars with masses around between 80 to 25 solar masses, they reach the iron limit, so they fuse material until they have an iron core, then they start collapse and generate a supernova. But for the other types of supernovae, things are a bit uncertain. So types 1B and 1C supernovae, they are called stripped envelope supernovae because they don't show hydrogen or helium, and that means that they lost their outer layers. But the way they lost the outer layers of the star is a bit uncertain. So they can lost it through a very powerful winds, and that would require a very massive star that is their progenitor that is constantly throwing the outer layers out, or they also could be explained by binary interaction. So companion star is taking out the outer layers of this massive star, and then this massive star would explode, but they don't have the outer layers of hydrogen and helium. Also for interacting supernovae, they require the progenitor star to be to shred many solar masses of material, so the explosion can interact and produce these narrow lines. So the main scenario is that they are caused by these massive stars, such as luminous blue variables. But the observations of environments, they do not fully agree with that, and I'll talk more about that later. So we are interested in trying to find what are the progenitors of the different types of supernovae, and what are the types of stars that generate these different spectral properties. One way of doing that is by simply looking at the supernova position before the star exploded. This was done in some cases, such as for this supernova, 2008 BK. So in this case, this is where this is the supernova image. They looked for images before the explosion. They found this star there, and after the supernova faded, they found that the star was not there anymore. And they confirmed that this was the progenitor of this supernova and that this was a red supergiant. So this is a type 2 supernova. But the problem is that this is we don't have that many observations of progenitor stars of supernovae, because we need them to be very nearby. We need them to be like with a good quality. And in most cases, they are type 2, so they are not stripped envelope or interacting supernovae. So another way of constraining the type of stars that give origin to the different types of supernovae is by indirect methods, such as looking into their environments. People have been doing that for a long time, such as the slide I showed before, where they looked for the different host galaxies of supernovae. And recently, more and more people were using integral field observations of galaxies to try to constrain better the environments of supernovae. So this was a work done by Luis Galbani and collaborators, where they looked into host galaxies of supernovae from the CALIPHA survey. So here I'm showing one image of the age alpha flux of this galaxy, and this plot shows one of their results. So this plot is a cumulative distribution, so it's like a histogram normalized. And what is important to see here is the values of the of that physical parameter at the supernova position. So here they are showing the age alpha equivalent width for these different supernova types. And we see that for type 2s and type 1 BC supernovae, they have very similar values to each other. And type 1a supernovae, they have lower values. And age alpha equivalent width gives us a sense of the age of that stellar population. So this is telling us that, well, type 1a supernovae, they happen in older stellar populations than type 2s and type 1 BCs, which is expected. So then came MUSE. So MUSE is this integral field unit at a very large telescope in the Paranal Observatory. And what is important about MUSE is that it provides this very high spatial resolution. So we can look with a very high spatial detail into the galaxies that hosted supernovae. So in this work of 2016, from again Luis Galbani and collaborators, they showed how powerful MUSE can be in the analysis of supernova environments. So here it's an example of one galaxy that they analyzed. These dark black symbols are all the H2 regions identified in the galaxy. Again, this is with a very good spatial resolution, and these are the supernova locations. So here they are showing again cumulative distributions of each galaxy in terms of metallicity. And in this case, because MUSE can provide this very good resolution, they could plot the properties for all the H2 regions in galaxies and also plot the supernova position here. So, for example, for one of these distributions, like this purple one, what they are showing is that, well, this supernova is in the most metal-rich regions of that galaxy. So then it comes my project. So this project is actually the first study of a large sample of core collapse supernova host galaxies observed by the MUSE instrument. We have 114 host galaxies observed. Here I'm showing all the supernova types that we have in our sample. Most of them are type 2s, but they are the most common core collapse supernova type. But we also have some numbers of, well, interacting supernovae, type 2Ns, type 1Bns, also stripped envelope supernovae, such as type 2Bs, 1Bs, 1Cs, and also one superluminous supernova. Here on the right, I'm showing the example of 3 galaxies that were observed, and this yellow square is showing the MUSE pointing in this galaxy. So this is a 1 arc minute per 1 arc minute in each galaxy. And another important property of this project is that all the supernovae were discovered by the ASAS-SN survey, which I'm talk a bit now. So the ASAS-SN survey is this all-sky automated survey. They have 5 units now around the world. So in the US, in Chile, in South Africa, and in China. And this allows the survey to be always monitoring the night sky. So they are always observing the night sky. And they have this untargeted approach, which means that they are not targeted towards a catalog of galaxies. So supernovae surveys, they usually use a catalog of galaxies. They are always observing the same galaxies, and they are trying to find supernovae there. Well, the problem with that is that you are always observing like more large galaxies and more metal-rich galaxies. And in an untargeted approach, you are discovering supernovae in smaller galaxies and fainter galaxies and more metal-poor galaxies, for example. The survey is almost spectroscopically complete in the sense that almost all supernovae discovered can have a spectrum associated, and this is allowed in part because the telescopes are quite small, so the events are always bright, and people can easily obtain a spectrum of that supernova. But that's important because when we have this untargeted approach and when we have a classification of this supernovae, we can do a more unbiased population study of these discovered supernovae. So what we are interested in doing in this project is looking in the properties of the H2 regions inside these galaxies. So here I'm plotting for one galaxy 3 slices, one in age alpha in green, and the other 2 in O3 and sulfur 2. So we can see here all the hydrogen emitting regions in this galaxy, and we can see the position of the supernova in that galaxy. And we are interested in the H2 regions because, the supernovae they are generated by these massive stars, and they don't have enough time to travel around the galaxy from the place they were born. So using H2 regions is actually a good way of understanding the properties where the supernova was born. So in this right plot, I'm showing the same galaxy, but now just the age alpha emission, and all these green crosses are the H2 regions identified inside that galaxy. So once we identify the H2 regions, we can extract the spectrum of each region and analyze their physical parameters, such as the metallicity here in the left, and the age alpha intensity in each region. And age alpha intensity can be translated into star formation, for example. So here we have this very nice, very nice information about the galaxy, where we see, for example, the gradient. We see where the supernova exploded, and that it was like in an intermediate metallicity in terms of the whole galaxy, and in a bright age alpha region inside that galaxy. So with all this information in hand, we extract the property at the position where the supernova explode. And to analyze this in a more statistical way, what we do is that we plot again this cumulative distribution. So we can compare the different supernova types, how they compare to each other in terms of these parameters. So here I'm showing the age alpha equivalent width, which again can be seen as the age of that stellar population. I'm plotting different colors here. So the blue ones are the type 2s, or the age-rich supernovae. Greens here are the interacting events, and the orange are the age-poor or the stripped envelope events. And here are all the different types divided. So one thing that we found with these results is that the age-poor supernovae, they are associated to the youngest H2 region. So they have the largest values of age alpha equivalent to width. And when we separate the different age-poor supernovae, we see that type 1c supernovae, they have the larger values of age alpha equivalent to width. And this is to say that they are associated to more to younger regions than type 1b's and type 2b supernovae. We also analyzed the star formation rate of these H2 regions. And we found that age-poor supernovae, they are associated again to the more star-forming H2 regions, as can be seen here. And when dividing the age-poor supernovae, again, type 1c supernovae, they present the highest values, higher than type 1b's and type 2b's. And again, in terms of metallicity, we see the same behavior of age-poor supernovae happening in the most metal-rich regions, if compared to type 2s and interacting events. In this case, type 1Cs and also type 2Bs, they happen in the most, in the more metal-rich environments. And one interesting thing that we see is that type 2Ns, they present similar values to type 2 supernovae, this result was observed before in other analyses of supernova environments. And it is curious because we expect these events to happen in more metal-rich environments than type 2s. But this could be telling us that they have a combination of progenitors, not only very massive progenitors, but also less massive ones that can generate this type of events. So we also looked for correlations between the light curve properties of these events and their environments. So we looked into the maximum magnitude, so the magnitude of the peak of the light curves, and try to correlate with the age alpha equivalent width, star formation rate, and metallicity. We didn't find any strong correlation. There's only a weak indication of a correlation for stripped envelope, where we see that the peak kind of anti-correlates with metallicity, but again, there's only a few events to be analyzed here, so we cannot conclude anything very strongly. And well, one important thing from this work is that we analyzed these 114 galaxies, and we have these properties already will make them available for the whole community. So we have these maps of metallicity, of age of intensity, of equivalent width, that can be used not just by supernova people, people who are interested in analyzing supernova environments, but also for doing extragalactic analysis of these galaxies. And well, after all these results, what are the implications for the progenitor stars, which are the thing that we are most interested in? And yeah, we see that the age-poor supernovae, they are associated to the more young, more massive, and the more metal-rich stellar populations. The type 2s and interacting supernovae, they seem to be associated to similar stellar populations. And the type 2b supernovae, they are associated with less massive stars than type 1c and 2b supernovae. So in this case, type 1b supernovae would be connected to binary systems because they are would be less massive, while type 1c and type 2b's could be connected to more massive single stars. And well, for a future work, what I plan to do is to estimate the occurrence rate of the different supernova types as a function of the environment. So to see which supernova happen with more probability in a given environment. We also plan to do this comparison with some stellar evolution models. And we plan to do this global analysis of all the age to regions within the galaxies. So yeah, that's all.
Okay, thank you. I would like to start something new today. I will push PhD students to ask first. I should have said that before. But if you are a PhD student, please, can you start? I mean, we need at least a couple or 3 questions from PhD students. So please. Hey.
Yeah.
So I'm not a supernova person. So the very first project you had, you're trying to see if this object was a supernova or something else.
Yeah.
Why do we care about that?
Why do we care?
Yeah.
Well, that's a good question. Yeah, so I think the most important thing is that some events, they are misclassified as real supernova, and they are instead like a stellar explosion. So in order, I think, to understand better both supernova and both stellar explosions, it will be interesting to tell them apart. Yeah.
Okay. Second by a PhD student, second question. Come on. Okay.
I think you probably said it, but why didn't your work include type 1A supernova?
Type 1A? Yeah, so we are focusing now on just on core collapse supernovae. So we are not analyzing any type 1A environments. Yeah. But maybe for the future, that could be something to do, yeah.
I can have.
Yeah.
Just because Christina is not that's the within the collaboration.
Okay, yes, she's doing that, yeah. Yes, because no, this was set from the beginning that we would analyze core collapse supernovae. Yeah.
Yeah. Okay.
I'm not a PhD student.
Yeah, but we got two already.
I had other questions, but now how can you do the same analysis with type 1 range where they're so old, we will have the scale the range to the regions. So you don't know the place on the metallicity, etc. Right? So
It's for him or
for everybody, because-
Yeah.
yeah. So the thing with 1As is that, as you said, they are all stars that have been moving, so they are not at the very position like or collapse, which come from the usually the closest or the one that is on top. But for cosmology, we have found these relations with the environment. right? So there's the brightness is not universal. So when you standardize the light curve, the peak magnitude of the supernova, there's some relation still with environment. Usually this is used, this has been measured with global properties. So more massive galaxies, so supernova are happening on more massive galaxies. They are actually less bright, but when you standardize with the universal method, they become overcorrected, so a bit brighter than those happening in low mass galaxies. So these have been studied with metallicity, with global properties such as metallicity, age, mass. And then there's some discussion that when you use the local environment instead of the global, these relations are even steeper than with global properties. So it's here you are doing physics of the explosion of the progenitor and all that. You are not, I mean, you could argue that those happening in more massive galaxies, if the galaxies are elliptical, they come from all populations for sure. And this could prefer some kind of progenitor scenario than the others, and then you can associate how well you use that object for measuring distances with the progenitor. You have to do a lot of steps here. But it's an observational fact that their relation with the environment. And studying the local properties, we have like more than 1,000 galaxies here. I would say there are actually more 1As than corpuscles, like let's say half and half, a bit more 1As. And this is actually the PhD of this person here.
My actual question was because sometimes you get a correspondence between 1B, 1C, 1N with the scenarios.
Yeah.
Interacting, it's interacting in the sense interacting in the environment or binary interaction.
No, it's interacting with the like a circumstellar material that the star ejected before it collapses. So it's a material that is around the star.
Okay,
Yeah.
So in the previous slide,
This one?
in the previous, yes, here, exactly.
Yeah.
The split table of supernova essentially. We have two scenarios. One is the weights, and one is the binary interaction.
Yeah.
With the end.
Yeah.
So from this kind of trend, can you tell whether this is consistent with? I suppose this tells you that it's more consistent with the stellar winds, right?
Yeah, the metallicity. Yeah, kind of.
But on the other hand, from the spectrum,
Mhm.
if you do modeling with the line emissions, suppose the environment that the supernova finds has been not there because of the history of the star. So if you have winds, it will meet the material will meet the expelled material from the wind. Or on the other hand, it will meet possibly envelope that was ejected by the binary direction. Is there a plan to do modeling of the different scenarios using spectral stars? Population synthesis are taken into account.
Yeah, I don't have that plan, but I'm not sure if people have done that before.
I'm not aware.
Yeah.
If you're looking at, well, if you let me answer.
Yeah.
So what you're looking at here is just that the brightest strip envelope conditions with low metals. This is all. So you have here several objects at the same time. So this is a population analysis, right? If you want to go to individual objects, you get the spectrum of that object, and then compare to models and all that, and then you can measure how much mass has been ejected before and all that, right? But here, what it's just saying is that those that are brighter, so the y-axis comes from the supernova light curve, actually. Brighter, they happen at low metallicity. Then the step through the scenario progenitors. I mean, this is just metallicity. Low metallicity means probably so the stellar winds depend on metallicity. So you have here that those that are brighter happen at low metallicity. This is telling you if all are due to stellar winds, those that are at low metallicity are brighter. That's all. but mass transfer in binaries also depend on metallicity, right? So it's telling you things about the two scenarios. Is when you compare these with star formation with other parameters that can tell you different, right? And if you study individual objects, you can then model, put in input binarity for this, and then compare. But we are not, I mean, here you actually are using parameters from the supernova, but you have not measured those in the spectra, or you are not comparing any spectral
No.
feature. So this is just
Yeah.
a population analysis. Right? If you want more detail on individual objects, I mean, the interesting part would be to look at those 3 or 4 there that are brighter and low metallicity, and try to compare some models, which one of those fit better, and then get 3 or 4 on the other end, and see that there's something different in terms of more physical progenitor scenario or something. But all this analysis is just statistical on populations. And most of the relations are, super cloudy. But is when you find someone that some relation that is very, so the relation is significant, statistically significant, is when it gives you a clue, and then you can go and start the physics.
Yeah.
Starting the range of 10 to 11 solar masses, they can explode due to electron capture because they form an oxygen and magnesium core. Do you expect any correlation with the environment in this case?
Correlation in the environment. No, I'm not sure. I don't know.
Those should be more associated. I mean, the right answer is that we don't know.
Yeah.
That's the right answer. I mean, as I said, this is, when you want to compare to progenitor models, it's more complicated because you have to, which supernova come from plate instability from this scenario?
For instance, it is suspected that the Crab Nebula is an electron capture supernova.
Yeah, but at high redshift, how many of them we can associate with those? That's I mean, that's the, we need to put a label. This is why ASAS-SN, which is this survey that is not very, very deep. It's down to 17 magnitudes or so, but it discovers everything up to down to 17 magnitudes. So you can do this population analysis. So all those, not the 114, but all the 400 or so that ASAS-SN has discovered down to 17 magnitudes is all supernovae that happen in this volume. And then you need the spectrum and a label. So you have the type. Then if you want to go to models and the explosion mechanism and all that, this is then analyzing object by object and saying this is the scenario or this other. But I mean, from here, I'm not sure what to answer.
No, in fact, it's a difficult problem because we are adjusting the border between separating the formation of a white dwarf and the supernova explosion. This is always a fusing situation.
Yeah, actually, you mentioned that there's a spectra for all the objects, so there's a lot of things that you can do, and then use the environment parameters to compare to, as I said, in the same answer, right? I mean, you can compare to models to all the spectra that you don't have here, and then anything that you find compared to the environment.
Yeah, because what I'm doing is just taking the classification, and I'm not looking like deeply into the spectrum. But yeah, that could be done.
So about the excursions, did you identify the excursions to the galaxy? Or
No, this was a code. The IFU analysis code.
Okay. So you use this code that actually identifies its.
It separates the age in the galaxy.
Okay, this is not the pilot.
It's similar. Yeah.
There are several versions.
Okay.
It's from an age alpha map, just found the blocks. So it finds the peak in the two-dimensional map, and then integrates up to a certain level. Then mask that region and look for the next peak and iterating all the time until you have these maps with the.
Because my question would be,
I mean, if there is any, you know, for example, distinguish them from small animals.
Yeah.
So, you know, we have confidence. You can do
That could be done, right? Like for supernova remnants instead of H2 regions.
Yeah, I mean, because also small elements can present a example.
Yeah. Well, that segmentation is used, and then you extract the spectra, you integrate all the spectra within the aperture.
Yeah.
That is the segmented region. And then it is there's some stellar provision synthesis applied there.
Okay.
But I'm not. You use a VPT to disregard those that
Also, yeah.
ionized by AGN, but I think those ratios for the are indicating that there's some supernova remnant shock or whatever. I think we are not using those.
No.
There may be
Yeah.
some. Yeah, there may be some contamination to check.
Yeah, that would be nice. Like, this will be from
Yeah.
And you said you had the spectra of most supernovae. What happens to those that you don't have the spectra? Use them? Do you classify them in a different way, or
No, we have spectra for all the supernovae.
is it like almost like most?
Is it most?
Yeah.
No, yeah, all of them.
Okay.
We have like good spectra, and they were classified.
Okay.
Yeah.
Okay.
Yeah, ASAS-SN has discovered like 2 feet per year, or during the last
Yeah.
8 years, like 500s, let's say.
Yes.
And the period, not the period, but there's classifications of 98%.
Yeah.
Almost.
Where did they come from? Like the classification? Like
Public classification.
Yeah.
Presto,
Yeah,
ASAS-SN,
follow-ups, yeah.
ASAS-SN itself. But this 114, all those have classification.
Yeah.
Otherwise,
All of
they're
them
not
are
used.
classified. Yeah.
So it's complete, almost complete in a sense, because it's not very deep. So it's bright. You can use a 1 or 2 telescope to like the classification. It's not like VLT or what.
Yeah.
How do you select your galaxies? How do you choose one galaxy?
So to observe.
Like,
Yeah. So for these observations, I think they try to observe all the galaxies that could be observed by the VLT, and well, that were bright enough that could have good observations. So between 2014 and 2018, which is the period of the supernovae, there were 440 core collapse supernovae observed by ASAS-SN, and from these, 114 were observed by MUSE. So given the observational constraints, those were all the galaxies that could be observed. Yeah. Yeah, and some galaxies, they are very small, so they are not that bright, and yeah.
Any other questions?
Yes.
Yeah.
I don't know
then
if there is
there
questions. Yeah.
Is there any questions here? No.
No, yeah.
Okay, so it's in the patio.
Right. Yeah. Yeah.
I understand. Thank you.